Welcome, everyone, and thank you very much for attending the latest seminar of the International Centre for Spatial Computational Learning. My name is George Constantinidis. I'm the director of the centre, and I'd like to thank also Andrew Boutros for organising the seminar series. Before we kick off, I'd like to introduce our speaker for this seminar slot. So our speaker is Mario Doumet. Mario is an MSc student in computer engineering at the University of Toronto under the supervision of Professor Vaughan Betts. His research focuses on AI acceleration and data flow architectures. And over the course of his master's, Mario completed an internship at Intel Labs Parallel Computing Lab, working on distributed machine learning training using FPGAs as smart NICs. Prior to starting his master's, Mario completed his BEng at the American University of Beirut, along with a year of research in collaboration with MIT Media Lab, where he helped in the development of the world's first battery-free wireless underwater camera. So I'm very pleased to have Mario give this talk. I've spoken to him before about some of his work. It's really exciting. And I'm really excited to hear more about what's going on at the University of Toronto. So over to you, Mario.
Thank you. Thank you very much. All right, so the title of today's talk is From Sparsity to HBM, HPIPE's Advancements in FPGA CNN Acceleration. I'm Mario Doumet, and I'll be presenting the work of not only myself, but also Matthew Hall, Mohammed Ibrahim, Marius Stan, and all of that under the supervision of Professor Vaughan Betts. Again, a lot of the slides are not mine. They're some of theirs, some from their thesis work, some from their papers. I merely curated them to present it to everyone here today. So with that, let's get right into it. So the context for this. I'll start with introducing the context for this and why HPIPE was created, what the literature looked like at the time, and then I'll get into HPIPE's architecture. Finally, I'll go into how we improved on that architecture with different improvements to really take HPIPE to the highest levels of performance. And finally, I'll talk about my own work and what's next for HPIPE. All right. So when you look at the context of the literature at the beginning of this project, it looked a bit like this. So there were lots of projects, but if you paid careful attention, you realize that a lot of them, all of these, are PE style and could be mapped to ASICs. They're not really leveraging the customizability of FPGAs. And for that reason, they're not something we want to try and replicate when we think of FPGA CNN acceleration. However, there's two on here that some of you might recognize that do leverage the customizability of FPGAs. They're both data flow style architecture and are both leveraging the programmability of FPGAs. So when we look at LUTNet, it has a 15% drop in accuracy, and that's not something we'd like to replicate. We'd like to get something closer to 0%. And for that reason, our work will be closest in style to FPGA ConvNet. And there's two main differences that we have with FPGA ConvNet. First off, FPGA ConvNet uses HLS, whereas we will use a custom compiler. And second, FPGA ConvNet doesn't implement weight skipping, and we think sparsity will come in useful with regards to improving performance, and that's another difference that we have with FPGA ConvNet. So let's look at the architecture. So we have a layer pipeline data flow architecture, but overall, there were two main possible architectures. I already mentioned them. There's a PE-based architecture, and there's a layer pipeline data flow architecture. On the left, you have the processing elements-based architecture. And that one relies on some general-looking processing elements with an on-chip buffer where the weights and activations are loaded in for one layer, and then that layer is computed, and then the output of that layer is sent back, and then a new layer starts computing with newer weights and activations. On the right side, which is HPIPE's architecture, there's a layer pipeline data flow architecture where all the layers are processing at the same time. So they all have their own weight buffers, and it's deeply pipelined. So each layer can start as soon as it gets its data, and that will have that will create all the process, and that will have all the processing elements working at the same time eventually once the pipeline is full. That's the one we decide to use. So let's look a bit deeper into that and the trade-offs associated with that. So we pipeline the computation across all layers, and as you can see on the right side in the picture, all three layers are computing at the same time. The first layer is processing the darker color line, and then the second layer as well, and the third layer is producing its first line. So all layers are computing at the same time. Now, what will that have as an effect on the weight bandwidth? That will require that all layers have their weights accessible at all times, and that will skyrocket the needs for bit weight bandwidth. So one solution that we came up with for this is to store all the weights on chip. Now that will require a lot of on-chip memory, but thankfully, something that does play to our strengths here is that we use low precision for the operands, not 32, sometimes 8, sometimes 16. And that will significantly reduce the on-chip memory requirement. The layers are connected together with the latency insensitive interface with coarse back pressure. The different type of supported layers that we do support in HPIPE are these ones from TensorFlow 1.x all the way to TensorFlow 1.16. And something I want to point your eyes towards is the fact that all of these layers are customizable to any activation tensor. And what this means is that for any size of activation tensor and any shape, we create a layer that's particularly tailored to that size. We don't instantiate more DSPs that we require than necessary. We create weight RAMs that are exactly the right size. And for something like a convolutional layer, we also have weight RAMs that are tailored specifically to the weight tensor shape. And for that reason, HPIPE really tries to max out the performance of each specific kernel in order to really get a whole pipeline that's really performant. So there's one more thing apart from the customizability of layers, and that's that each layer also has parameters. So on top of the customizability to the shape of the kernel and the activations, there's configurable parameters. There's two configurable parameters and one that's fixed. So the one that's fixed is the activation width, which we set to the maximum. But the two that aren't fixed are the input channel parallelism and the output channel parallelism. Just to get an idea of what input channel parallelism looks like, you can see it on the right. So when it's 1, there's only one multiplication per cycle that gets accumulated. When it's 2, there's 2 of them that get accumulated per cycle, and when it's 4, there's 4 of them. Now, clearly, as you increase the input channel parallelism, the time to complete the operation reduces, so the performance goes up. And the reason we need these parameters will become obvious very soon. When we look at the different layers, some of them have have more weight, some of them have more multiply accumulates than others, and overall, different layers have different needs. And what that means is that some layers are going to be faster than others, and some layers are going to be slower than others. However, in something like HPIPE, an entire pipeline is only as fast as the slowest component. So if you look on the right-hand side, you have this picture with red bars that show the latency of individual layers. And clearly, some layers are slower than others. And those layers will be the bottlenecking layers when looking at the entire pipeline. So what we want to do is even out the latency of all the layers to make sure there's no one big bottlenecking layer. And in order to do that, we increase the parallelism settings, so the parameters I mentioned previously, in order to even out the latencies of all those layers. So I'm going to play the video, and you're going to see how we're going from 700 DSPs to 5,000 DSPs, but then you'll see the latency of all the layers is pretty much the same. Yeah, like so. And this is one of the main strong points of HPIPE, where it's able to predict the latency of every layer and really tune the parallelism settings of every layer correctly. Now, I said that we tune the parallelism settings of every layers, and there's hundreds of layers, and each of them is customized to the exact tensor shape, activation shape, and also to the weight kernel shape. And that will require automation. So can we use HLS? Well, we could, but HLS is a really great boost for productivity. But when you really want to get that extra last bit of performance, it's not really the best. So ideally, we'd like a domain-specific compiler, and that's what we end up using, that's tuned for performance, also aware of physical effects, and can target new AI-focused FPGA features if needed. That way, we'll be able to port HPIPE to newer AI-focused FPGA without too much effort. So with that, I'll start talking about HGen, which is a custom hardware generated that we created specifically to generate the hardware for HPIPE. So HGen takes in a TensorFlow graph and produces hardware. So it produces for FPGAs the Verilog, the memory initialization files, the timing constraints, and the Cordis settings. You choose the parameters, just like in the picture on the right here, you can see the DSP target is 5,000, and we specify BRAMs of 1,000. And then HPIPE, all it does is it takes this and it generates, with the TensorFlow graph, all the output files that you require. The total build takes less than 4 minutes for a 5K DSP ResNet 50 model. The Quartus compiles, per usual, will take up to 2 days. But luckily, the change of weights can be done without a new Quartus compile. So if you're doing work in quantization or you just want to change the weights, you can do that without compiling the entire thing all over again. So with regards to the graph construction, individual layers are hand-coded by us in RTL++. That's our custom Python to Verilog library. And what HGen does particularly well after that is that it tunes the individual modules to achieve a very high Fmax through 2 types of optimizations. First, logic optimizations, and second, physically aware optimizations. Now, most of you are probably well aware of what logic optimizations are, but maybe do not know necessarily what physically aware optimizations are. So I want to dive a bit deeper into that and give some more insight as to what HGen does exactly. So one such example of a physically aware optimization is fan-out optimization. So in general, in something like an ASIC, a tree structure is a very efficient structure to distribute data. However, on FPGAs, wires tend to be slow and registers are really cheap. So instead of using something like a tree structure, we'd rather use something that's serial, as you can see in the bottom left figure, to distribute the data. And while that might require additional buffering, it ends up being more beneficial in the long, the bigger the distribution chain is. However, sometimes we still want to use the tree if the fan-out is high and the tree has low span. So HGen very smartly chooses which one of the 2 we need to use depending on the distribution network that we ask for. Another optimization that HGen does is it optimizes the RAM mapping. So instead of relying on Quartus's RAM mapping, we have our own RAM mapping that allows us to get better fan-out control and higher Fmax. So let's look at how these 2 optimizations perform from the perspective of Fmax and improving Fmax. So when we look at Fmax, it's 394. When we use the fan-out optimization, it drops to 392 and the register count increases to 700. So we don't think we achieved much. Well, let's wait a bit. At this point, the critical path isn't really determined by the distribution. It's more so that of the M20Ks in the RAM mapping. So by improving on the RAM mapping instead, we can improve Fmax significantly at a relatively modest cost in the increase of M20Ks and registers. And it's really after we achieve that the fan-out optimization really shines. So when we combine it after the RAM mapper, the 2 optimizations stack, and that's where we see the real benefit. And the Fmax jumps to 571. And overall, we can see that we got a 45% Fmax increase through physically aware optimizations alone. And these are just some examples of what HGen is capable of doing and what it does. And I thought it might be good to show it. All right, so let's get to the sparsity part. So HPIPE achieves 0 skipping at 1/4 the cost of prior work on FPGAs. So you might ask, why sparsity? Well, if you look at the graph on the right, you can see that for at 80% sparsity, there's barely any drop in ResNet 50 accuracy. And at 90% sparsity, the drop is relatively minor, so you might be able to deal with that. And for something like sparsity, assume you have 90% sparsity. For us, the advantages are twofold. Because we store all the weights on chip, if we use sparsity, then we can get up to a 90% decrease of on-chip memory, and also up to a 90% increase in throughput if the 0 skipping is implemented correctly. So we have a double the incentive to get sparsity working here. So there's 2 ways to do that. First, there's a scatter-based convolution, kind of like what's seen in SCNN, where you multiply sparse weights by the input activations, and then you get all the combinations of that, and then you get all the outputs, and then you scatter the outputs to get accumulated. Now, that does leverage both weights and activation sparsity, but it requires the scattering of outputs which are higher precision than if you were to scatter inputs. And also the accumulation is hard to do in place, and so you would need a big RAM with rotating addresses. And what that means is that scatter-based convolutions overall are relatively hostile to FPGAs because they don't really leverage the FPGA benefits, and they're not as suited as we would hope. So what HPIPE uses is instead a gather-based convolution. So we gather the sparse weights and then multiply them with the dense activations to get the outputs. While that does leverage only weight sparsity, we are gathering lower precision inputs, which tend to be less than half the precision of the outputs, and the accumulation can now be easily achieved in place. So we don't need big RAMs in order to do that. Moreover, the weights are known in advance, so we can balance the different RAMs with weights, knowing the sparsity pattern in advance to make sure there's no one RAM that's significantly more loaded with weights than the other. All right, so let's look at the results. First off, HPIPE looks a bit like this. There's different layers and different colors, and it's a data flow style architecture, so data kind of flows through the chip and then and goes all around. So let's start with the dense results first, before we look at the effects of sparsity and how it helps us. So we have dense mobile net V1, where we outperform NVIDIA V100 on throughput, and we have a bit worse of a latency. But nonetheless, that's still very impressive. When we look at dense mobile net V2, we have more than 7x the previous work with regards to throughput and even better latency. Now let's see just how much better we can get if we use sparsity. So we're going to look at a sparse version of ResNet. So we're using an 85% sparse version of ResNet. And here we get close to 4,500 images per second, outperforming a batch 8 V100 GPU, and outperforming the throughput of brainwave optimistically scaled to the process nodes of the Stratix 10 and the FPGAs to the Stratix 10, and even the other architectures. So as you can see, the sparsity did give us quite the improvement over the dense versions. And so we really have a very performing pipeline that can process CNNs in a very efficient manner. And at this point, we're left wondering, can we do more with it than just classification? And so what we try to do is extend the pipeline to object detection. So object detection requires the drawing of bounding boxes around a picture. And effectively, in terms of computations, it means there's basically a neural network, a CNN with some extra layers that draw the boxes. And then there's a non-maximum suppression unit after that. So we use HPIPE as that first part here that takes care of both the yellow and the blue operations. And then in collaboration with Arizona State University, we take their pipeline NMS module and extend HPIPE with it. And we try to look at the performance that the entire pipeline gives us. And the results are non-equivocal. We get 2,167 frames per second with a 2.13 millisecond end-to-end latency for the COCO validation set. That's 5.3x higher throughput than the best prior work in Mobilint, and 3.8x lower latency than best prior work. And finally, the mean average precision score exceeds the MLPerf quality target of 22. So we see that HPIPE can successfully be extended to other applications beyond classification and will still perform relatively well. So at this point, we've pushed the performance of HPIPE and the way the architecture is optimized, and we're wondering if there's anything more we can do to get even more performance. And something that we thought of was the AI-optimized tensor cores on Intel FPGAs. And we want to see if we can leverage these to get even more throughput from HPIPE. So let me give you an introduction of the Stratix 10 and X tensor block and walk you through what it looks like. It looks a bit like this. It has 96 inputs and 75 outputs, and 3 25-bit accumulators, so 3 outputs. And we want to try avoiding adding any pins to the block, because adding pins to a tensor block on FPGAs is very expensive. So how do we add more compute without necessarily increasing in the number of pins? Well, let's start slow. At the beginning, we have something like this: 3 multiplications that will fill out the 75 outputs, and we require 48 inputs. So at this point, you might wonder if we're done, because we used all the outputs. How can we pack in more computations without having more outputs? Well, you can start adding restrictions, and those restrictions will allow you to pack in more multiplications in the tensor block at a certain cost. So one such example is vector mode, where we have 6 and 8 multiplications. And so we're using double the inputs, but we're using only 25 outputs. And the way this works is by accumulating all 6 outputs together instead of letting you use all 6 outputs. And yes, there's a restriction on the way the inputs are handled, but it's a trade-off we're willing to make if we're going to get double the multiplications. So following this logic of adding one restriction to get even more compute out of the tensor block, what's the best we can get? Well, there's something that's called tensor mode, and it looks a bit like this. It packs 30 int 8 multiplications and requires 80 inputs and 75 outputs. Now you might be wondering, what cost did we pay to get to this? Well, there's a few restrictions, but they're not as bad as you think. So there's an 80-bit input that's shared across all 3 dot product engines that's broadcast to all of them. So already half the operands are copies of each other. So that's the black line, the black arrows that you see over here. And second, there's 3 80-bit operands that have to be preloaded through various methods. Those are the ones in the blue, red, and green arrows. And that will take multiple cycles. So these are the kind of restrictions that you have to deal with in order to get those 30 int 8 multiplication. So for HPIPE, we look at something like vector mode and like, oh, that's great. That's exactly what we need. We're accumulating data anyways, so it's a good fit for us, and we're able to support sparsity with it. And that's great. Now, with something like tensor mode, the question is, can we use it? And are the restrictions just too much for us? And so we set out to discover exactly just that. And we concluded that we can use it, but only for dense convolutions, and it requires additional logic for preloading. So let me get right into that. There's 3 preloading methods, but I'm only going to talk about 2 of them. So I mentioned there were 80 inputs, and there's a maximum of 96. So there's 16 that have gone somewhere. And those are the ones we use for side input preloading. So we use 16 bits per cycle. And so to fill in all 3 ping pong registers, that requires 15 cycles. Another method of preloading is to use an empty tensor block at the top that won't be used for computations and use its input 80 bits to cascade through all the way down to the lower ping pong registers. And that will require 3 cycles to preload the entire block as opposed to the previous 15. One more thing I haven't addressed is we still don't know what to preload. We're multiplying activations and weights, and we don't really know, should we preload the activations or should we preload the weights? So with all these questions in mind, we set up to run simulations to find the best preloading scheme. We ended up with something like this, where you see the activations are really the ones you want to preload, and you want to broadcast to weights. Nonetheless, there's still side input mode and cascade mode that still perform the same, which are these 2 that you see on here. So we run some more, so we look at some more data, which is the activation buffer memory estimates, and we see that they're still similar in that aspect. And so we ended up going for cascade preloading simply because it is simpler to implement, and it doesn't require fragmentation of the activation buffer to have it close to every tensor block. We only need one that we put at the top tensor block, and then the data gets cascaded through. So with this in mind, let's look at the results that we get. First off, we compare the performance of the different operating modes of the tensor block. So we get something like this. Now in DSP mode, we only use 2 out of the 3 multiplications to get it closer to what a standard DSP looks like. In vector mode, you can see we get close to the 3x peak improvement that we could have gotten. So vector mode is utilized very efficiently. And tensor mode doesn't get quite close to its 15x, but we still get significant improvement from it in the form of 8x, 6.8x, and 4.8x. So how does this translate to throughput, peak throughput? Let's look at MobileNet v2. In MobileNet v2, we get close to 28,000 images per second, outperforming a batch 128 GPU. We get 17x higher batch 1 throughput than a V100 GPU, and 1.3x higher batch 128 throughput at 3x lower latency. So we really beat the GPU in all aspects in that regard. The results are similar for MobileNet V1 and MobileNet V3, where for MobileNet V3 we get close to 34,000 images, and for MobileNet V1 close to 27,000 images. All right, so we've shown that we can leverage the optimized tensor cores successfully, but there's still some limitations to HPIPE. With HPIPE, the parameters have to fit on chip, so we really can't accelerate the largest CNNs. Moreover, sometimes a chip just doesn't have enough DSPs, so it might limit our performance. So one thing we thought of is to partition HPIPE not across one FPGA, but across multiple FPGAs. And that would preserve the HPIPE architecture, where we still leverage the customizability of each FPGA, but we now have more memory available to us, and we can use more compute resources in order to have lower latency and higher throughput. So the partitioning flow that we developed looks a bit like this. It optimizes the graph, it allocates resources to each layer, and also assigns the nodes to different FPGAs. And finally, it checks the legality to make sure we didn't assign too many layers to one FPGA that doesn't have as many DSPs as we would hope. So what are the results? Well, the experimental setup looks a bit like this. We have 4 FPGAs connected together with 100 gigabit Ethernet. And the Ethernet communication is taken care of by the Pegasus Ethernet modules from CMU, by Jipeng Zhao, from Professor James Ho's group. But that's not the main point here. We just want to look at the performance of HPIPE when it gets distributed. What kind of speed up does it get? And we get linear speed up. So for MobileNet V1, we get half the latency, double the throughput. MobileNet V2, half the latency, double the throughput. In going from 1 to 2, and then for ResNet in going from 2 to 4, half the latency and double the throughput. So at this point, we've kind of circumvented the memory issue, and now we can scale HPIPE to as many FPGAs as we want, and get double the performance, and get more performance and more memory. However, one thing that we haven't done is we haven't decoupled memory and compute. Right now, they're tied together, and a network with 10x weights would require 10 times more FPGAs. So what are our options here? When we look at our current architecture, we try to look for the different ways that we can use external memory or something that's not on-chip memory. So there's off-chip DRAM, and there are HBM stacks. I kind of spawned the answer here, but there's a very good reason for that. So when we look at off-chip DRAM, it has a very high capacity, but relatively low bandwidth. When you look at HBM, it has 32 times less the capacity, but 32 times more bandwidth. And I said it before, HPIPE, because of its layer pipeline architecture, will require way more bandwidth than an average processing structure, the processing architecture. So we really end up going for HBM here just because we need that bandwidth way more than we need the capacity. And 4 gigabytes is already 3 orders of magnitude higher than what we already have. So it's not going to be a limiting factor in any way. So we end up going with HBM. Now, what we want to do is reduce those gray boxes over here. That's on-chip memory. We want to reduce that to be able to support larger networks on one chip. So there's 2 ways to do it. We can offload the activations to memory, or we can offload the weights to memory, or we can offload both to memory. And it would look a bit like this. So in the same way, we ran simulations in order to know exactly what was best for the Stratix 10 NX tensor blocks. We're going to do the same thing here. But first, I want to run you through an introduction of HBM and what it looks like, and what kind of performance we can get from it. So an HBM2 stack consists of 4 DRAM dies, 2 channels per die, and 2 disjoint pseudo channels per channel. Each channel supports 128-bit DDR data bus running up to 1 gigahertz. Effectively, what you need to remember is that there are 16 pseudo channels with 0.25 gigabytes each, and a bandwidth of 16 gigabytes per second per pseudo channel. All right. So with this in mind, we set up to characterize HBM. We characterize HBM, look at the read latency, the write latency, and then the read efficiency and write efficiency. So for the read efficiency, we see it's, let's look at the write values just because we were going to utilize high bursts. So for the read efficiency, we can get close to 95%, so something between 90 and 95%. For write efficiency, it's closer to 80%, but that's still okay. The latency is close to 140 cycles when we're operating at 350 megahertz. And you can see the bounds for maximum latency and minimum latency around it. So what does this tell us with regards to the question we're trying to answer? Well, the read latency is 140 cycles. That means offloading activations to HBM probably isn't the best idea, because as we go from one layer to the next, we'll have to write to HBM and read from HBM, and then that'll take 140 cycles. Right now, it's closer to something like 5 or 10 cycles. So it's significantly more than we currently have, and it's not something we're willing to do. Offloading the weights, however, will end up being beneficial for one main reason. The access pattern is deterministic and can be known in advance. And so if we're willing to decouple the weight reading logic from the rest of the pipeline, then we can prefetch the weights hundreds of cycles in advance and have them buffered at the inputs of the tensor blocks. And that's something that we can definitely do and we set out to do with HPIPE. One more thing, read efficiency reaches 90% and the write efficiency reaches 80%. But that's only when the burst counts are high. So we need to make sure we're leveraging data that's contiguous in memory to really get more of that efficiency. Luckily, weights are very contiguous and get read entirely every time from start to finish. So that's something that won't be a problem. So let's run a more detailed analysis to see just how much of the weights we can offload to HBM. So we get this graph over here that shows all the networks. And if you look on the left, at 100% throughput, we can offload close from 40% to 75% of the weights, depending on the network. And that means that we'll be able to remove, say, 75% of MobileNet v3 from on-chip and store it on HBM without affecting the throughput of the main pipeline at all. Now, if we really want to get all of the weights off-chip, we can go closer to 25% throughput, where at that point, we can offload all of the weights to HBM and still get that 25% throughput. Now, at first glance, it might seem like a bad idea, but with HPIPE's performance of 30,000 images per second, a 4x cut will still have throughput, like an inference rate and a throughput of close to 8,000 images per second. So it's not as bad as it sounds. So how did we go about implementing it? So the implementation is in progress. I'm currently debugging it. It works sometimes, doesn't work sometimes. But it looks a bit like this. You have the prefetching logic at the top that's decoupled from the main pipeline, and then that ends up sending the addresses to HBM. And you have at the bottom the buffers to cover latency. So we fill those buffers in advance and make sure that as the tensor block starts reading those weights, we have enough buffer space that the HBM can pick up and send weights back into the buffers in time. And all right. So there's also some physical awareness issues with regards to HBM and placing. So just like we leveraged physical optimizations before, physical architectural optimizations before, there's an opportunity to leverage some more here. So when you look at the layers on the left, there's conf2d16 that's somewhere in the middle of the chip. However, HBM really is on the top of the, it really is at the top and at the bottom. So if we want to move conf2d16 to HBM, we'd have to move it either at the bottom or at the top. And when that does, it'll move it to the top, and the place and route engine will end up putting it there. But also layers closest to it will be in its vicinity. So that means we need to be very smart with regards to which layers we pack in HBM, where we pack them in HBM, and which layers we pack together in HBM. And these are challenges that we're currently facing and that we hope to have solutions to in the very near future. So that's it with regards to what I'm presenting for HPIPE. And there's one more thing regarding future work that I'd like to mention, and that is neural architectural search. And you might wonder, well, why NAS? And the answer is simple. We have hardware that can process sparse layers, hardware that can process dense layers, and with neural architecture search, we can figure out exactly which layers to sparsify and which layers not to sparsify in order to maximize throughput. We can also look at which layers to quantize to lower precisions. Because HPIPE produces layers at any precision, we can choose to willingly decrease the precision on some layers to utilize less resources, and we can get double the benefits if we store these layers in HBM, where we can get more weights in a single read if we lower the precision. So that's why we think neural architectural search can help. So thank you very much for listening, and I'm willing to take any questions.